Hi, I'm Dalton, and today I'm going to be talking a little bit about Physics 2211's Lab 2. So in this lab, basically what we did is drop an object that would have observable air resistance on it. So in my case, I chose a crumpled up piece of paper, as that's something that's light enough that the air will affect. Looking into a little bit more, the system in this case is going to be the piece of paper that was dropped, and the surroundings are going to be everything else, or in this case, just the air around it, acting as it's going down. So there were a few basic principles used in this. The main one and the main purpose of the lab was to observe air resistance and gravity. So normally we know that gravity is going to be pulling something down, but now we're trying to look at the fact that air resistance is basically pulling back up on it and resisting it going down. And in addition to that, we use the velocity update formula and the position update formula for all the calculations. And then to get more specific with air resistance, for this we use BV squared, where B is basically just a coefficient for air resistance. So first of all, I'm going to show the tracker model. So this was generated just using the tracker software and documenting the position of the object as it fell over the time, down from initial height of what was around 1.8 meters. So now we'll move on to look at the computation with only gravity. So for this one, essentially just in the code, the net force was only the force of gravity. So we were seeing a straight down line, but we also noticed that in the time frame it should have taken to fall, it went past the zero, which that goes to show where air resistance definitely is happening and that gravity is not the best way to just look at this. We need air resistance also. And that brings us over to with the air resistance. So now we're looking at the start from around 1.8 meters, and over the time frame, as we would expect, it hits the ground and doesn't magically go through it. So then here's a quick comparison for all the graphs. And as you can see, the tracker and the one with gravity and drag are almost exactly the same, which is to be expected because the tracker was real world observation and gravity and drag are what would both exist in the real world. And then looking down at the only gravity line, we can see that that's different than all the rest, which is as we expect. And the position's going negative, which doesn't really make any sense in this scenario. So here's some of the code that was used. This is just from GlowScript, and the first one is representing without the air resistance acting, which we can see in the net force only having mg. But then we look down to the other one, we have mg plus the equation that uses the b times velocity squared, which is accounting for our air resistance and the true net force on the object. So what does it mean? We were asked what models would predict a terminal velocity, and in this case, that's going to be the one with air resistance, because really all terminal velocity is when the force of gravity and air resistance equal each other out, and there's essentially a zero net force acting on the object. So therefore, we're not going to have any more acceleration, and it essentially locks into a velocity, and terminal velocity is just the word that applies to that concept. And it would only be that one because the others don't have air resistance. So there's nothing to ever make the net force different or like go back to zero rather than just be mg. So then another question we were asked is, would there be a terminal velocity change if the object was thrown with a non-zero initial velocity? Simple answer is no, and we can look at that here. The graph on the left, I altered the GlowScript code to give the object an initial velocity of negative 0.2 meters per second. And then the one on the right, the initial velocity was zero, just like how I actually dropped the object. And in both cases, we see the velocity goes down and essentially flatlines at around negative 2.3 on both graphs. This goes to show that terminal velocity is like a set thing for an object. There's no matter how fast you throw it, it's not going to reach a higher terminal velocity because the air resistance is equaling it out, and it's due to the acceleration of gravity. So the initial speed you're throwing it with is not even a consideration. The only thing that could affect is the time it takes to reach its terminal velocity. But as we can see here, it's going to be exactly the same no matter what initial velocity it has. And that's about all. Thank you for listening.